is also involved in this.
Yeah.
So that will be covered by my colleague.
Yeah, Mr. Vivek.
Yeah, so he is a expert in HFSS for ANSYS. Okay, and he is my colleague. He is based out of Bangalore office. So he will continue with the BMS part.
Okay, sir.
Yeah, over to you, Vivek.
Yeah, Mr. Vivek,
thank you, Kailas.
Mr. Vivek, very warm welcome to you.
Thank you, sir. Thank you very much.
Yeah, very good afternoon. We would like to have today's your session. So let us start with battery management system.
Okay, sir.
Okay,
Is
sir.
my
The
screen
overview
visible, sir?
Yeah. Just put it
Yeah.
into the slide mode.
Yes.
Slideshow.
Okay, good morning, good afternoon, one and all. Today, this session will be about the battery management system. Till now, you have been having the sessions on electric vehicles, where you will be knowing, like you'll be mostly dealing with the power electronics part. And now, in this particular session, what we'll see is how we can manage battery power, if the fluctuations are there, how to control it. Will be maximum using the embedded system with this. And the most prominent tool of ANSYS in embedded system is SCADE, and that how to use that particular system and how we move on with that system, that I'll be giving a short glimpse on it. Basically, why we need a battery management system, what it happens, because of poor battery managed system, battery management, there might be sequences where we can move on to drastic accidents. Okay, first thing is thermal runaway, then the short life of the battery or the loss of capacity within the range. In some cases we might say like the battery capability might be high, but basically we can take a simple system of a mobile phone. Like while buying, we can see it could withstand for a whole day if we use it regularly also. But as we keep on using it, the capacity of that battery, not also the capacity of that battery degrades, and also the management system, whatever the ICs which have, that also degrades. If that battery management system is also not there, then it will degrade it as soon as possible. Okay, then the last thing is the longer charge time. Using this, we can whenever it is in we shouldn't be like battery has been much used for a long time. For that sequences will be consequences, we will be using this battery management system. What battery management system ensures is safety, performance, cell life, and interface. Like whatever the drawbacks which I said earlier, that are the things which a battery management system can provide to you. And the main function of BMS, we can say, is monitoring of state of the cell, like voltage, temperature. Like voltage in the sense, like if any over voltage or the low voltage, like battery signal, like low battery signals or high band, it is fully charged, those kind of while charging, those kind of automatic signals we can receive using battery managed system. And the temperature, like usage of over usage or at the particular time, that indication that will be maintained, like till particular temperature. Okay, a coolant, like when to activate a coolant, and when the coolant is not working properly at that particular time, what to do, like those kind of signals we can receive from this particular battery management system. And basically this particular battery management system will maintain the overall the condition of that particular battery, how it is and how to move on with it. That will be useful. And next is monitoring of the state of high voltage system connectivity. Like if it is connecting to any over voltage or high voltage systems, how whether as I said earlier, if any overflow of current is there, then it will indicate. Then the next thing is calculation of state of charge and state of health. As I mentioned earlier, what is the state of charge, like how much the state charge is and how the battery level is. Okay, then the next thing is balancing between cells. We will be having number of cells within the battery. Within that, like within lithium ion cell, we can't we can't take off all of the powers. At that particular point, we need, like in each and every battery cell, the battery management system will take care of it. And the last thing is establishment of high voltage connections between HV batteries and this thing power strains and charging systems. Whatever the interconnector or interfacing is happening within between the battery and the other components, that will be taken care by battery management system here. Here this particular demo, like a system where we will try to showcase you is end-to-end demonstration of demo of the overall system, the SBU capabilities, and that is for the development of ISO 262 262 complaint BMS. What are the complaints which has that ISO particular mark, that will be overcome. It includes functional state analysis within we'll be using a Medini analysis, which is capability of ANSYS SCADE architecture, and the system architecture with SCADE, like what are the functionalities and technical aspect which we have, and the textual requirement for BMS software control. What are the softwares which we incorporate with this particular embedded system, that we'll see in the second part, and the software controllers and the prototype design, which will be like the first part we'll be doing with SCADE architecture. Then the second suite comes where SCADE suite and testing. Using that, we'll be seeing what it happens for that particular prototype or the design, and we'll verify it. Then the last is the overall system simulation using twin builder, like with battery management, like battery, and with battery management system, we will be using we'll be transferring into the ANSYS twin builder. From that, we'll like whole EV vehicle model can be ensured. And the next thing is BMS support software functions. What are the highlights of it? The SCADE what are the softwares which could be included with SCADE capabilities that will be showcased. And the whatever the BMS software that needs to be integrated with the existing, like whatever the BMS software you are how to say is, what are the in embedded if in a controller, what are the softwares if you are trying to incorporate in BMS, that should be supported to the twin builder model as well. And in BMS system, here it is, the first thing is system architecture, then the function, next we'll see the functional safety, then the software textual requirements, what are the software which we require, then the software design, and the overall simulation. These are the main things which we will be concentrating on. First thing is like a functional safety analysis with Medina. Okay, here we have three components, like battery, switch box, and ECU. This particular components are the base components. This will be making it in this, we will be designing it in using Medina. And then the external interfaces are SOC and SOH, and the cooling and heating system, where once you get to know whether it is cooling heat is heavy or low, that kind of an analysis. For that we have an external interface here, and two categories of functions are there, which are maintenance of SOA and operation, and the emergency disconnect. Like if something is short circuiting in between, that will be getting disconnected. And this is like electric vehicle level function and associated malfunction. Here you can see the function overview. Here this is from a battery state, what are the functionalities and what are the things which can be out of it. At that point you can see this particular statements will be coming, like whether no or not, how to say is no, the state information is broadcasted for each kind of terminal. Each BMS will be whatever the system we had built here, for each and every state it will be showcasing what is the functionality or the malfunctioning, if it is happening, like if there is any malfunction, you can see here, calculate the value, like it is very low. Then the next thing is what it happens when it comes to the same, like when we integrate some software safety goals and safety requirements. If there is any hazardous event have been identified during the stationary charge, okay, at that point corresponding safety goals and the safety requirements are defined in this particular part. Here you can see some valid information, battery vent and gases, or like thermal is running away, some like indications you can see. Once you build the BMS system, you can see what the battery state that will be indicating in this. Then the next thing is control software design. In this we can see like the voltage monitoring is the first thing. How much voltage has been given, like there might be like in switches due to malfunction there might be over voltage we might receive, like to like while charging how the voltage monitoring has been done, that we will be using required switch current like control voltage 1 and switch control voltage 2. Here in this module, like we'll be having the channels voltage, like for each cell we'll be having channel voltages, and here the unit will be of 0.1 millivolt, and it will the range from 0 to 55,000, like okay, 16 units will be there. The same will be having for the control 2. Then here you can see like control voltage inputs whatever we are giving here, and the control voltages we are getting in the software. Like once we had built the system, what are the software requirements it needs, like we need to set a voltage controller where it could control the input high input voltage kind of thing. Then software simulation and testing, the next part is, once we come into it, once this overall system is done, we can see here the simulation of this particular voltage out of range, then warning, and the second system we can see voltage out of range when it is critical. Like if it is true, it will go in this sense, like we'll be setting a threshold warning for low also as well as high also. Here once the voltage is passing, like we can keep it as like once you are connecting your charging point, then you can say like if it goes beyond the threshold voltage, you can say like this is not connecting properly and it won't be charging properly. The same way, if it goes beyond over voltage is there, it will indicate the threshold voltage limit will set here. Based on that, if it is okay, then it will be charging, or else it will give some warning. This is a system for alarm, and this is an like a modelized system where we can control our threshold voltage for each and every, like we can keep we can vary this particular voltage variation, and we can see what is the type of voltage we are getting, like it is getting charged, whether it is low or high, what is the hysteresis in it. And the same way you have an alarm modeling, like whether it has been battery has been filled, or those kind of analysis can be done. The same can be exported, took out, and we can use this particular test coverage. And the last one is system simulation. Here we can see once this battery BMS, here you can see this BMS is connected here once to the battery, and then based on that battery the overall system will be connected. Like this part everything would have been covered earlier. This is the part where battery management system needs, like this is especially we can make it using SCADE, which is a tool in ANSYS. From that we can move on. Like I would like give the session to Kailash so that he will be going for battery session separately.
Thank you so much, Vivek. You will be staying or you are leaving now?
Yeah, I'll be here. Yeah.
Okay, yeah, because if any questions are there, then it'll be better. Okay. Yeah, can someone confirm if audio is there? Sorry.
Yes, sir. Yeah, audio is there.
Screen is visible?
It's coming. Yeah. Slideshow
Yes,
is
it is
ready.
audible.
Okay, okay. Okay, so I hope you got an idea about the battery management system. So we'll start with the battery thermal management system now, and I'll just quickly start with this. So in this session, we are going to understand the battery solutions. What are the different models that ANSYS is having that can help you to do the simulation for the battery, and what are the fluent capabilities. Then we'll see certain customer stories, and then we'll actually go through the tool, and we'll see the one demo for the thermal analysis of the battery model. Okay, so as we have already discussed, so ANSYS is a market leader, and it's like 2 times larger than any of nearest competitor, and it's only focus on the simulation part. Again, ANSYS is a platform which provides the best of breed simulation across all the major physics. Again, there is material libraries are available for the ANSYS, as I have already discussed, and again it provides a solution for the various physics, as we can see. Now, again, there are various customers of ANSYS that we can see worldwide. So in out of these customers, there are various automobile customers which are actually using the ANSYS solution for the battery simulation or EV purpose, in which I can take a name of like Volkswagen. So with or in other vehicles or other companies, you can say Tesla, and also they are actually utilizing the ANSYS simulation for the battery thermal management or BMS. Or even other parts as well. So definitely it is quite useful in AV sector. Then first of all, basically, so what is a battery? So battery is a source of the electric power consisting of one or more electrochemical cells with external connections for powering the electrical device, such as we can say the depending on the devices or requirement. So in this uh, picture, you can see the one of the EV you can see, and this is the part where actually battery cells will be mounted over here, so on the both sides. So in basically, if you see in the EV section, you will be, I think it is a hybrid electric vehicle, but if you see in the EV, you'll not be having any specific engines or anything in the front or back. It will be completely empty, and only in the middle side you'll be having this battery cells mounted. So those will be in thousands, thousands of the cells will be mounted together in this complete battery packs. Okay, so this electric batteries, electric car batteries, it's an energy accumulator that stores the electricity for the transmission to an alternator or continuous current engines. So now talking about the battery simulation, so what are the different simulation that we can perform over here? So this is the first video, so you'll get an idea. So here it is.
There's a race underway in the automotive industry, and there's no time to lose. Today, hybrid and electric vehicles have come to the forefront as viable alternatives to conventional internal combustion engines. The battery is becoming the single energy source of these breakthrough vehicles. It's only a matter of time until electric-powered vehicles become the industry standard. Before it does, technology must for top efficiency, increased capacity, and assured safety, all at a competitive cost. Leading the charge in this endeavor are automotive engineers who must completely rethink how they approach powertrain design.
Batteries are, in a sense, a new research and development topic. So all the combinations of parameters have to be carefully studied before a viable gap battery can be prepared.
As many people know and research has shown, whoever gets to the market first with their product will gain a greater part of the market share, and they will become leaders in that market, and everybody else plays catch up.
They're turning to multi-physics-based simulation solutions from ANSYS to gain foresight into how their designs will perform before prototyping takes place. The multi-physical, multi-scale, and multi-parameter complexities of battery technology development present a unique challenge to automotive engineers. An integrated simulation approach to overcoming these challenges is an absolute necessity for companies that want to stay in the race.
As automakers are developing electric vehicles, developing battery challenges that they need to overcome.
The timeline in battery development is very short, relatively speaking. We have about a 5-year window by the time that you want to get something implemented in time you get it into production.
So there are three main differences between a battery and other traditional automotive components. And in short, those three differences can be said to be multiphysics, multi-scale, and multi-parameter.
What we do at ANSYS is we say, okay, let's model that battery on the physics-based level. Let's look at the interaction between the electrochemistry and the thermal interaction and create a behavioral model that captures that, that behavior, and now take it up into the system.
There is a tight coupling from the powertrain level all the way to the nano level.
Simulation reduces the overall development cycle so that you can get your product to the market faster. Electrically, thermally, mechanically, we have the best-in-class solvers to solve those individual physics. So the advantage of simulation is that you don't have to build it, you don't have to test it, or as many iterations. You can get great insight in your design, optimize it, give you greater reliability, greater efficiency, and have a better product to the market sooner than your competition.
For the companies in the race, the potential payoff is enormous, but so are the risks. Going to market with flawed, inadequate, or suboptimal designs simply is not an option. Simulation software from ANSYS will get you there faster, safer, and at a lower cost. ANSYS simulation software creates a virtual representation that accurately shows behavior and performance, resulting in a shortened development cycle and products getting to the finish line first. The revolution is underway, and it promises to change everything. ANSYS, realize your product promise.
So with this, I hope you got an idea how the battery simulation plays a very important role in case of EVs or whatever the HEVs that we have. So definitely we supposed to understand how this can be beneficial for the EV sector. So now let's talk about the multi-physics, multi-scale, and coupling nature of the battery simulation. Okay, so first of all, battery simulation that involves the multi-physics, multi-scale, and the couple of them, right? So this makes battery one of the most interesting and challenging simulation. So here. Okay, so concerning physics, electrochemistry is the most important most important and fundamental battery. Simulation models based on electrochemistry are also called as physics-based models. So this okay, yeah. So then this simulation models, those are based on electrochemistry, are also called as physics-based models. So the length scale of 3D electrochemistry in a battery application is approximately 10 raised to minus power 4 meters. Okay, which is extremely small as compared to the size of just a battery cell. So for lithium-ion batteries, so this P2D Newman P2D model that could be used to model the electrochemistry between the electrodes, which is still short of even a battery cell. So due to the intensive computational resource requirement for the electrochemistry calculations, so various reduced order models, that is ROMs, ROMs approaches are also available in the ANSYS. So with the help of model reduction, we can study the impact of different particle shapes of the battery electrochemical performances. Then Then let's move to the next part, that is electrical. So battery is primarily an electric device, right? So the most common use model for the predicting the battery electrical performance is the battery equivalent circuit model. Okay, that is ECM. uh, Equivalent circuit model, that is ECM. Okay, so this ECM models are behavior models. So these requires so-called HPPC data for the model parameter identification. So this data can be taken either from the experimental, or you can get this data from the ANSYS twin builder as well, where you can simulate it for the real-time condition. So this is a configuration from the electrochemistry models, and then we can get this HPPC data over here. Okay, then for this higher frequency applications, ECM parameters are determined from the electrochemical impedance spectroscopy, that is EIS data. Okay, so due to its fast performance, ECM is often used to simulate a battery module, or even a pack with as many as 500 cells as well. Okay, then the capability to be able to couple the ECMs with the third party tools, that is FMUs, that is functional mock-up units. Okay, uh, with these third party tools, it even often viewed as a welcome feature. Means like that, we can say that that can be an add-on feature, so that you can easily transport this data to any third party tool as well, where you can do the further processing, and this search becomes quite possible through this FMI or FM, that is functional mock-up unit. Then last but not in the list that we have, that is thermal performance of a battery. So even though lithium ion batteries have relatively high thermal efficiency, that which is nothing but greater than 85%, its sensitivity to temperature makes it critical to manage the temperature correctly. So for the lithium ion batteries, it is often required to have in cell temperature variation of less than 4 degrees, and the cell to cell variation should be less than 6 to 8 degrees, right? So battery thermal management simulation using CFD is a mature application for CHT, that is conjugate heat transfer. So but the system integration of battery simulation demands faster and compact models, thermal network models, which is one of the model in the battery models pack in the answer CFD, and the reduce order models, that is ROMs. These two models plays a important role in this thermal analysis aspect. While simulating battery single physics, it's already challenging, so we have to consider a coupling of different physics. Electrochemistry is a fundamental physics behind the batteries, but if electrochemistry works as we desire, then there is no need to couple different physics, since electrochemistry itself, it includes all the physics. But as I said, due to small length scale associated with the electrochemistry, so it is a practical simulation tool only up to electrode level at most, so you cannot go beyond that. So therefore coupling of different physics sorry different physics becomes necessary for any application that is beyond a pair of electrodes. So when it comes to battery cells, so definitely you have to go for the coupling of multiple physics together. So electrochemistry models could be used to create a performance data from the this for the example, this HPPC data, so which can be taken from the either twin builder. Okay, so this is very valuable when the battery prototype is not available, and therefore HPPC test is not possible. So electrochemistry could also be used as a sub model for heat generation for the thermal models. Okay, then which is in turn could provide the electrochemistry models that require temperature to update the material and transport properties. The huge discrepancy in the length scale for these two models demands a very ingenious way of coupling. So battery so here battery EC sorry, battery ECM is available. So electro uh, chemical models. Okay, so one could couple with the ECM with the thermal model. So coupling is possible in between these three different models as well. Okay, so for this electric or thermal coupling, an electric engineer that is typically is more interested in the electric aspect, and whereas if you talk about the thermal engineer, so that will be more interested in the thermal aspects, right? So such requires demands to simulate tools to be flexible enough to focus on either electric or thermal, even though the coupling is same in the both. So the then as if there is not enough, then there are important suitable application that do not fit with any of the schemes. So battery aging is one of such schemes that we have. So one could either model the aging under the electrochemistry as additional physics or sub model. Another approach is to model aging based on the test data. So they are both useful with the different focus in mind. So battery thermal abuse or runaway is another example. So this battery thermal abuse could be also be modeled under the electrochemistry part. So these all different types of simulations related to batteries are possible with the help of ANSYS over here for the battery thermal management systems. Okay, then talking about the battery meshing geometry and meshing. So here you can see you can easily create a complete battery pack with the help of a modeling tool that is ANSYS SpaceClaim. And then as we have seen yesterday in fluent meshing, so we can very easily create a mesh. Here you can see the model that has no 14 series and one parallel configuration. So this complete battery module that has 14 cells in series and one in parallel configuration, and for this 4.3 million mesh count is created with the polyhedral elements very easily. Okay, that this battery packs consist of the 12 modules. So this complete battery pack, you can see this 14 ps1 configuration is for each cell. Okay, then all cells comes together and they creates a battery pack over here. So you can see this becomes a complex geometry wise, as well as it becomes complex to generate the mesh. But here ANSYS space claim and ANSYS fluent meshing that can help you to generate a better model and create a better mesh very easily. Another tool that I have already explained yesterday, so that helps you to copy paste the meshing. So if you see in the previous slide, so if you see these different cells are there, those are identical to each other. So what you can do is you can create a mesh for one cell, and then you can do the copy paste to the remaining cell. So you can finish the mesh as fast as one cell. Okay, so means, so if you whatever the time required to create a mesh for a single cell, that is only important. So for the rest of the cells, you can just need to copy paste the mesh. So that is how it will work very easily. Then as I again explained yesterday, so we have already added the battery models in the model section in the ANSYS Fluent. So previously it was an add-on tool which supposed to be called through the TOI command, and now it is not required. So we can easily call the model through this direct GUI commands. Then talking about the thermal management, so what is exactly this thermal management is? So thermal management system that keeps the cells and the models within the specified operating temperature to ensure the optimal performance. So the temperature, as I already explained, the temperature should not go beyond certain limit, or it should not even go even down below the specified limit. So that makes the that reduces the performance of the battery. So this thermal management system that keeps cells and modules within the specified operating temperatures to ensure the optimal performance. So that again, that pulls heat away from cells quickly to eliminate the safety issue. So what are the challenges over here? So there are various temperature effects are there in the battery, like depending on the range, charge, safety, and the life. Then high temperature that creates a greater risk for the thermal runaway. Then trade-offs in the thermal system design between the cost, weight and size, and efficiency. So like we should even optimize it for the weight, cost, and as well as for the efficiency over it. Then again, we need a assurance of performance safe or safety, which is needed under the range of driving and ambient conditions, maybe geographic. So what it can be like, it's like in various road conditions also there should be assurance of the safety for even for the various driving ranges. So that should be there. So that is a challenge that we have in the for the EVs, battery sections. So here we have the battery models. As you can see, this comes with the electrochemistry of a battery component, so which are specialty model that enables to derive the electrochemistry thermal sensitivity of the cell and electrode. So here we can even check the battery performance. We can model, and we have certain models to determine the battery performance degradation with the aging over here in the ANSYS. So we face various challenges in the industry that can be solved with the help of ANSYS CFD. First one is a thermal abuse or safety simulation that can be very easily performed in the ANSYS Fluent. And then again, temperature sensitivity and cost effective cooling design. So these also can be simulated with the help of ANSYS. Now, for this CST analysis, as you can see, we can get this kind of results. We can get a complete temperature results with joule setting. Then we can get the current density, magnitude, contours, and various post-processing results are possible. Then talking about the cold-plated CFD for this heat transfer coefficient that can be obtained for each module over here. So if you see this complete battery pack, so how the temperature is varying from inlet side to outlet side, you can say that if you consider this particular battery pack. So here from the inlet to outlet, how the temperature is varying from inlet to outlet, and how we can optimize that all those things can be very easily done over here. So CST can be a function of time modeling varying at a different flow rate. So those things can be easily modeled at different mass flow rates at different varying temperature conditions as well. Then as you can see here, ANSYS helps to keep the track of the complete thermal or electrical cells individually. So like you can get a complete detailed results over here, and you can easily simulate it for the complete battery pack. As you can see, this is a battery pack, and that is simulated for the thermal analysis over here. Okay, and this is the pack when the short circuit is happening. Okay, so this is the temperature contour for the battery pack cell, battery pack module for the short circuit condition. Then next one is the electrochemistry. So what is the electrochemistry? So it is a that's the physics behind how the battery operates and performs. So the cell performs depending on the cell materials. For that we have a ECM models in the ANSYS Fluent. Then what are the different challenges that we face over here is first one is the cell cost that can be 50% of the battery pack cost, right? Then again here different requirements are there based on the application, like EVs or HEVs that dictate the battery chemistry choices. So maybe you have to say like the different choices based on the applications, like based on the range, what are the peak power is required, what could be the low to high temperature, and the battery, how battery is going to perform under those conditions. So all those things need to be taken into the consideration. Then cell design that impacts the ability to meet the performance requirements. So definitely cell design also need to be optimized. Then again, there are other challenges in the electrochemistry, like battery electric and thermal performance is that is controlled by the electrochemistry, right? So this electrochemistry model involves the solving of highly coupled nonlinear partial differential equations. And then this battery aging that requires the 3D electrochemistry modeling. Then battery structures is highly complex, right, which need to be resolved in 3D electrochemistry modeling. So for that, what ANSYS can help, how ANSYS can help. So we have Newman's P2D electrochemistry, which is implemented in the ANSYS Twin Builder and Fluent as well. So you can make a use of this for this electrochemistry models. Then again, 3D electrochemistry models are also available under the using the UDFs, that is user defined functions. Then 3D Newman's electrochemistry, which is implemented from the 2019 R2 version of ANSYS. Then again, 2D Newman electrochemistry models could be used as a sub models in the Fluent's MSMD, that is multi-scale, multi-dimensional models, and that can be used over here for the battery model. Then, as I told, this is the lithium ion battery electrochemistry model that is available in the ANSYS itself. Okay, so this is a for battery manufacturers that need to be fit the amount of power into a, battery pack that achieves the unprecedented size, weight, and cost goals. So this Fluent includes a detailed electrochemistry model that enables you to optimize the lithium ion battery cells, for example, to explore the improved anode materials, etc. So these things are very easily possible with the help of this lithium ion battery model. Then next part is ECM, that is the equivalent circuit model, which ANSYS is having. So here have electric vehicles or hybrid electric vehicles have peak power like, the power requirement is high on the higher side, right? So this EVs and HEVs demands good even they requires the high discharge or charge rate performance. Again, EVs and HEVs demands good low temperature performance as well, and relatively low energy density associated with the batteries compared with the ICs that causes the short circuit range. So there is a demand to model the portability among the different platforms as well. So ANSYS capabilities are there to accurate ECM parameter identification using the robust proprietary fitting algorithm provided by the ANSYS specifically for ECM identification, that is equivalent circuit models identification. So this ECMs are temperature and SOS dependent for by default. So you can get 1 RC, 2 RC ECMs for both the possible tools. Then we can easily optimize we can do the customization, for instances low temperature ECM and C-rate temperature ECM data can be easily availed through this. Again, you can export this particular data into third-party tools, like you can see the Simulink, where you can go for VWMS simulators as well. Then another model that ANSYS is having, that is reduced order model, and that is useful for the different engineering challenges, like battery cell performance, which is very sensitive to temperature, right? So as I already said, so temperature variation within the cell need to be less than 4 degrees Celsius. Then again, the cell to cell temperature variation that need to be less than 6 to 8 degrees Celsius. So for that purpose, we need a compact design to utilize the limited space as well. So, and again, it should be cost effective cooling design. So for all these purpose, ANSYS is having the best in class CFD for the battery thermal management that scales linearly using no, you can solve with the using 200 cores with HPC, and that can even you can even include the joule heating also inside this. Any queries? I hope someone's mic is on. Yes, for EVs and HEVs, again, it depends on the batteries. The requirement will be different for EVs and HEVs. But yes, the power demands will be need to be considered in that case. Okay, so then we have here flexible meshing strategy, conformal and non-conformal meshing, which are available over here. Again, we can even create a mesh very quickly over here. Then ROM technology, that is reduced order model technology, that makes a transient simulation time compatible with the system simulation. Again, you can this ROM also support the third-party tool like through the FMS. Okay, so I hope these are the different models that we have over here. Then another model, that is electrothermal coupling model, that, which is where thermal is main focus over here. So this, in this case, battery thermal performance need to be two-way coupled with the battery electrochemistry or the electric performance. So many orders of magnitude, length, scales, discrepancies between the electrochemistry and thermal need to be done. So joule heating, that also need to be included for the bus bars for here. Then thermal abuse, short circuit, nail penetration, that involves the additional multi-physics challenges. So for this purpose, MSMD battery module, that which is there inside the ANSYS Fluent, that can couple electrothermal at a cell and a battery level, or we can say the module or pack level. It can be coupled. Then this MSMD, that includes the flexible electrochemistry submodels, NTGK, ECM, and Newman P2D models. So these models we are going to see in the tool itself. Then again, built-in electric potential solvers are there for the joule heating. Built-in thermal abuse and short circuit models are also available under the MSMD, that is multi-scale, multi-dimensional models. Okay, then talking about the another part, that is a crash test, because as compared to the other or IC engine vehicles, electric vehicles used to have a greater risk at the time of crashing. So for that purpose, we have ANSYS LS Thane tool that can be very helpful over here, where you can combine the multiple physics together, like mechanical, electromagnetics, electrochemistry, thermal, and CFD, and then we can even perform a crash test with the help of this with the help of LS Dyna software, and we can easily find out the impact of the explosion over there and other things. So we can see this is one of the actual case study from the Ford, where they have simulated the done the battery simulation for the safety modeling using the LS Dyna. You can see the reference over here. So this, we can say, one of the customer success story from the Ford itself. Then we have another success story from the VW racers. So let's have a look at this.
There he goes. Ramanjuma. Holy smokes. That is one extremely fast car. This is some of the most exciting racing you will see anywhere. He broke the 8-minute mark. You've made motoring history today.
Yeah, I know. We're going to celebrate today, and then we look to the future.
And after Pikes Peak success last year, Volkswagen Motorsport decided to try this year to get the electric record here in Nürburgring.
It's nearly the same kilometers as in Pikes Peak, but as you have here much longer straights, you will need much more battery, and that here is probably one of the biggest challenges.
We need a lot of simulation to find the right concept, otherwise it's too much testing. If you have to test everything on the track, you don't have enough time. So simulation is really a key factor.
The battery cooling is a project on its own, because battery cooling during driving is essential, because we have to stay within a temperature window, and to optimize the cooling, this is done with the help of ANSYS.
Now the simulation is one of the biggest tools we can use to prepare what we have to do in terms of battery management, in terms of braking, in terms of downforce.
We needed a simulation partner for battery capacity and so on, and ANSYS has filled in this role perfectly. We build on the relationship we started for last year's program, and it's just getting better and better, and so we're also very happy that ANSYS is on board for the rest of the year.
The challenge is so amazing and it's so great that we for sure will all push in the same direction to get this record.
Fantastic performance today, and with 6:05 I think everybody can be really proud on itself.
Okay, so I hope you got an idea. So this is a success story from the Volkswagen Motorsports. Okay, so definitely EV, or we can say the simulation, plays a very important role over here. So with this, I have finished with the presentation. We'll start with the demo for this battery thermal management system. So these videos are available on YouTube itself. You can just check it out. So I couldn't get your question for how much temperature it is permissible. Okay, so we'll start with the demo part. I'll just show you the problem statement first, and then we'll continue with the demo. Okay, I'm just sharing the screen. So this is the model that we are going to simulate over here. Again, the mesh count over here that you can see, it will be very high, and mesh is already created for this model. And again, I am not solving it in real time. I have already kept this model or problem solved, as I cannot complete the simulation within a few, within an hour, we can say. So that is the reason I have already kept it solved, and then I'll directly show you the results part. Okay, so I'll just run the video so that you can easily understand. I'll be explaining all the steps necessary which are required over here. Okay, so the problem statement here is we have to do the conjugate heat transfer analysis that we have to perform on the module with the configuration of 14 SP1, that is 14 cells in parallel, sorry, in series, and one in parallel. Okay, means it's that battery pack has only one parallel combination. Okay, and the mesh for this model is already been created over here, and we are as you can see, 4.3 million polyhedral cells are created for this particular problem. Okay, so with this, we'll start with the actual problem. So I'll just share this screen. Yes, I hope this screen is visible to you. Okay, so let's start with this So first of all, you just need to launch the answers Fluent directly, since we already have the mesh with us, so no need to be worry about the creating a mesh. So you can simply launch the Fluent itself directly. Okay, so just go to start and search for the Fluent and launch it. Okay. And once you have launched the Fluent, now you have to go to the solution mode over here. In the Fluent, we have three types. One is the Fluent matching, second one is the solution, and third one is the icing part. Okay, so we are going for the solution. Icing is another separate module we have. Okay, so meshing is already done in ANSYS Fluent itself, but we have the mesh file directly, so no need to go for meshing again. Okay, so we are directly going to import the mesh file. So just select the solution mode, then give the process number of processors. Let's say 4 I have given. You can enable the double precision for better accuracy. Make sure that 3D is selected over here. Okay. Which simulation? So we are using the CHT, conjugated transfer analysis, over here in ANSYS Fluent. Okay. So after giving the processor, just start this Fluent itself. If you want, you can give the working directory, and you can just browse a folder where you wanted to work on this particular topic. Okay, once it is done, click on start. So it will launch the ANSYS Fluent now, and then we can start creating the model. We have to import the model. Okay, so to start to import the model, you have to go to the file, and then you have to go to the read mesh file. Okay, and then it will ask you to browse the mesh file over here, and then we can import it. Okay, so select the model and click on open. So as I told, it's having 4.6 million mesh count. So the time taken even to load the model itself will be more. You should have some good high in system, so that you will be not get any delay in the while importing the model. Okay. So I have already edited this video and made it fast forward, so you can see it is still taking this much time. So it's a really lengthy procedure, or we can say it's time taking procedure over here. Okay, so you can see it's still importing the model. Sir, I am using ANSYS Fluent software over here. Okay, I'll type it for you.
Kailas sir, sorry to interrupt you.
Yes, sir. Please go ahead.
Hello. Yeah. Why are we using only polyhedral elements? Is there any specific reason for that?
The reason behind that, with a less mesh count, you can get more number of nodes, so you can get more better or detailed results. Generally, we used to go for hexahedron elements, right? In 2D, we used to go for the quad elements. So mostly in the most of the softwares, maximum elements that is supported like hexahedral. But if you see the complex geometries, hexahedral elements might not fit correctly for most of the problems. So in that case, we try to go for different models. So here polyhedral elements, those are fitting best over here, and that those are giving the better quality, we can say, better mesh quality as well. Okay.
So are we using higher order elements in polyhedral?
No, we are using normal elements. Higher order, again, that will again give add-on, so that will be again time consuming. You can go for that as well. So that is actually, I don't think it is available and in ANSYS Fluent, but in ANSYS, sorry, in Workbench matching, it is available, higher order elements.
So how much percentage? How much percentage of experimental results are closing with this matching with this modeling techniques?
See, it's like matching with the modeling technique is something. It depends on various factors. I cannot say it's just depend on the mesh you create, but it depends on the mesh in grid independence test. It depends on the various actual conditions. So how much ever you try to simulate with the actual condition, somehow we make some approximations. So definitely that again affects the results. Maybe we can say any operating condition. So generally when we try to apply, like we are blowing air, if we take an example of wind tunnel, and we are moving a fans with a speed of let's say to achieve a speed of 30 meter per second, but whether actually those are reaching or not. So those things, when we go in actual condition, that makes certain difference. So but still you can achieve up to 90-95% accuracy, again depending on problem to problem. So it varies from problem to problem, as well as from the like other things as well, like conditions and everything, and how accurately we apply those, so that also depends. Okay.
Okay, sir.
Sir, one more question. Is it required that we should go for HPC for this kind of simulations? Is it possible to do it in the normal systems?
Yes, I have done it in on this system itself, which is a normal system. It's not like we should necessarily go to HPC, but it is suggested when you have very less time and you wanted to do some multiple cases you wanted to run. So it's like when you go for HPC, you can get faster solutions. So it's completely up to you. Again, if I can tell you, this all depends on the various factors, like how much solution accuracy you are expecting, what is the time that you have to solve that particular problem, and along with that, whatever the computational power that is available to you. So it actually depends on all these three factors. So generally now in this problem, I am not worried about much about the accuracy, because I just wanted to show you how we can get the results. But if I want accuracy, I think then 4.6 million mesh, that could not be sufficient. I might have to go for some more mesh, or I have to perform the grid independence test. So
Yeah,
again,
that's what.
that depends on the problem to problem. That's what. If I'm worried about accuracy, I have to follow the multiple steps to make results more real time. So that takes time. So again, when that itself is going to take a time, and again, if you have very less computational power, then time taken will be more. So depending on the conditions, we can say. I have solved this problem on this system itself where I am representing now. But the time taken for me, it was like around 1.5 to 2 hours to complete the whole simulation. This importing this mesh file itself, it took almost 15 to 20 minutes for me, but I have shortened over here. But with that, you can get an idea how exactly it works. So it depends how, what is the problem. If you have very simple problem, then you don't need to be worry about it, like you have some 1 or 2 lakhs of nodes or some 5-6 lakhs nodes. So that is not an issue. You can easily solve with some 16 or 32 GB RAM computers or laptops that we have. But if you have like millions of mesh, so definitely, now if you can imagine, for just to import the model itself, it is taking 20 minutes for me for 16 GB RAM. So when it is actually solving the problem, so how much time it will take. So that is how we need to understand, and based on time availability, resource availability, we have to work. Okay, I hope you got the idea. Yes, so
Yes,
there
sir.
is a
Thank you.
question. Yeah, thank you, sir. Is it a paid version or free? Sir, if you wanted to learn the software, then it is free. But if you wanted to use it for research purpose, then it is paid. Because ANSYS student version is available for learning purpose, but that cannot be used for the publications or any teaching activities or anything else. But
It is
yes, if
not
you,
locked, right?
yes.
It is not locked. Number of nodes are limited, no?
Yeah, again, number of nodes are limited in case of student version. Yes, that's what, because it's only for learning purpose, not for research or any other, right? So that's why it has some node limitation as well. So for mechanical, if you see, we have 32,000 node limits, and for CFD we have 5,20,000 node limits in the student version. You can very easily download it and you can practice it. It's just for those who are new to ANSYS, and then you can definitely go for it. Okay. Yes, so we'll start with this. Okay, so as you can see, this battery pack is completely imported over here, and then we have to go for the next step. So we have to follow the certain steps to first check the mesh and everything. Okay, then go to the scale, where you can just check out the scaling. If you want, you can scale it, or if you want, you can change the length. Then perform the mesh check. Once the mesh check is done, here you can see it's still showing checking mesh, and once it is done, you can view the report quality, where you can understand the mesh, whether there is some changes need to be done or not. So whenever it shows a any warning over there in the mesh report quality, then definitely you have to go back to the meshing tool, and you have to refine the mesh, or you have to improve the mesh quality. Because if you are getting the error over there, then definitely we can say the mesh will not be good over there. Okay, so then you can go to the display. Now here you can understand the various components, or you can say the uh, parts that battery pack has. Okay, so if you see, various walls are there, connectors are there, pins are there, positive and negative terminals are there, different cells are there, fins are there. Okay, so if you see, we'll start with this is the fin. You can see fin walls that we have over here. Okay, then uh, then you can see the different tabs that we can see on the bottom side. They are the connecting, these are the terminals on the those tabs. Okay, so like positive and negative terminals that we have. Then Again, few more tabs. These are the connectors. Those are joining the cells together. Okay. So if you see generally in even in toys also, right? If we have, or in you take a remote of a TV, right? Television remote. So that used to have two cells, right? So on the back side, they'll both two plates will be there. Those will be connecting to each other, right? So they are like connectors. So they are transferring the energy, right? So they are making the circuit complete. So that's how these connectors are also available over here. These are the various cells that you can see. This particular model has 14 cells. Okay. So this is the complete battery pack. Okay, so you can see on the top side various connectors, terminals over there. After that, now we have to go to the models battery, and here, as I told, this is the battery model that we have to enable to solve the battery
Sir,
model. Yes.
I'm just curious, what is the size of this battery pack?
I have not checked actually the dimensions, but it will be. I think here you can see in the coordinates. Okay. The thickness is it's like a 200 mm is this thickness. Vertically it is like almost 1.2 meters, and the in the Z direction you can see thickness is also around so width is also around 1.5 something meters. So we can get it from this coordinates, minimum and maximum coordinates. It's in meters. Yeah.
It's a very big. It's a big.
Yeah, it's a big itself, and actually the thing why it has created multiple the multiple we can say more number of mesh, that it consists of multiple elements inside that, and it each component will be meshed separately, right? So and according to that component size, the sizing of the elements in that particular component will be changing. So that is the reason it will create more mesh. And
So you are
since yes,
okay. So you're using a kind of shared topology.
yes, share topology will be used over there. Yes, like even share topology, and you can say conformal meshing will be used over. So those things I hope we were there in yesterday's session. So that is already I have shown you yesterday, right? So there we were having option to select whether it is consist of only solid and only fluid domain and solid and fluid. Along with that, whether we need to enable the share topology, and so all those options are available in the Fluent's meshing
Yeah.
watertight geometry workflow. That
Thank
yes. Is lithium phosphate model available in ANSYS? Not direct model. Direct model is not available. It's like lithium ion or potential battery models which are available over. Okay, so you have to enable the battery model over here. Once you enable it, it will show you all the models that we have discussed during the presentation, like this MSMD, then CHT models. All those things can be seen over here. Then circuit network, CST coupling. So all those things you can see over here. Okay, so you can see When it is enabled, you can see all these different models over here, and that again NTGK, Newman P2D. So all these different models based on the problem, as we have discussed, like in which case which supposed to be used. So all these models can be seen over here, and based on problem you can enable the required model. So here you can see CST coupling is selected over here, and with the Joule's heating effect. And then now we have to select the active zones and the passive zones over here. So all the cells, those will be acting as active zones over here, and all the tabs and connectors, so those will be acting as a passive zones. So you have to use this command to filter star cell star, so it will select all the cell models over here, and you just need to click on this select all option. Sorry. Then again in the passive zones also you have to go to this filter, first select stars, tab star, and select all the tab. Okay, so these are the like connecting tabs, they are connecting the batteries together. Okay, and then click on select all, and then again type a new name, that is star connector star, that is star con star you can type. So that will filter again to connectors part, and again select all else, and those all will be the passive components over there. Okay, so star con star, as you can see. Now click on again select all, total I think 56 zones that should be selected. So you can see when cursor is moving over there, 56 out of 88 which are selected. Now if we click on display passive zones, so that even you can even observe those zones in the display itself. So you can see, so these are the passive zones. Okay, so these are the 14 cells that we have over here. Okay, and then you can view the passive components. So remaining all, we can say those are the passive components. You can see the connectors, terminals, and the components. Okay, so these are all the passive components that we have. Then after selecting this different zones, then you have to go to this third tab, electric contacts, where you have to select the negative and positive terminal over here. So terminal N and terminal P that you have to select. And with this we are defining the battery. Now with this software should understand what this is the battery or specific battery. Now when we say print this battery system connection information, so it should print that 14S1 P1, so that should be printed over here. So you can see on the bottom side number of batteries stages, series stages are 14, number of batteries in parallel per series stage is 1. So you can see it is printed exactly. So what it means, software now understood what exactly that battery pack is consisting of. Okay, so that should be selected properly. Okay, as you can see over here. Then in the model parameters, now we have to give the values or the energy source, like how much each cell is going to provide the energy. Like here we are considering the 10 watt from each cell over here. Okay, and the total electric current that we are giving, that will be 100 amperes. Okay, so we have to provide all those details. Done. So for all 14 cells, we have given the energy source of 10 watt, and then we have to give the electric current of 100 ampere. And with this, we have actually applied the battery model over here. Okay, and just click on OK, so that all the settings should be applied. And after this, we have to create the materials for the different components over here, and it should be very no, you have to apply all the conditions very precisely. If any condition is wrong, then definitely it will lead you to wrong results. Okay, so we have to be very careful while doing selection to apply the material properties as well as to apply the boundary conditions. Okay, so I'll just take it forward. Okay, and next thing is to apply the material. So you can go to the physics, and there you will be having option to apply the materials. Okay, so go to this create edit. Now here, first of all, we have to assign a material that is active material. Okay, so change it material type, change from fluid to solid. Okay, and change the name to active material. And you can change the chemical formula as well. Now we have to take all the material properties that we are using for the battery pack. So nothing I am considering from my end. It should be completely given data. So we are giving the specific heat of 1224 joule per kg Kelvin, and then we are giving the orthotropic thermal conductivity in the directions like 132 and 32. Say okay to this, and then again go to the next step. Give the electrical conductivity. Okay, like this we have defined the material that is active material for active components. Okay, just click on change create and say no to override with the aluminum. So we need even aluminum material will override, it will be added over the aluminum, and aluminum will be replaced. So we don't want to do that thing, right? So we have just replaced it. If you go to material and in the solid, now you can see active material is added over there. Okay, and then now we have to add another material for the foam and for the plastic component. Okay, so just double click on this material and select the aluminum and click on edit. Okay, so here again change the name, let's say to foam, and then change the chemical formula, and then you can change the material properties for the foam. Okay, so let's say it's density is 320 kg per meter cube. Okay, and then CP is 2000, and thermal conductivity is 0.08. Okay, and again click on change create, and again say no to override with the aluminum. Okay, again create another material for the plastic, and first change the name to plastic. Again change the different properties. I'll just keep this. Okay, and just click on change create again and close this. So all the materials are added now. Again add one more material, that is copper, which is directly available in the answers library. So just go to create edit and go to Fluent database, and then from there select the copper material in the solids part, click on copy, and close it. Okay, so you can see copper material is also added over there. So total 5 materials that you can see over here which are added, and now we have to make sure that we'll assign these materials properly. Before that, these materials, if you want, you can just save it in user defined database. Okay, so if you wanted to use them in further in the future, so you can just save them for the future use in the user defined database. So go to this create edit option again, and then here we have user defined database. You can browse the location where you wanted to create the database. Okay, you can name this, and then just need to say okay to this, and it will ask you to create a database over there. Say okay to this, and it will ask you to create one. So say yes, so it will create a database over there, and then from there you can very easily import the material. So well, first you have to copy the material from the cases. So select all the material except the air. Okay, and you can just save all of them. Okay, on copy, and you can see materials are copied now. So means if you wanted to use these materials in future, so you can make use of it, no need to create it again. Okay, then once this is done, click on close, and now we have to assign these materials to various cell zones, means like various components. So for that, and again you have to go for the filters option over here, and we have to assign the materials to similar kind of components, right? So first of all, let's say we'll assign the material to cells. So for cells, we have to select the active material, right? So select any cell over here, click on edit. Okay, and here change the name to active material, apply and close it. Now similarly, we have to copy this material from this cell to another. So click on copy, select the material for which you have changed the properties, and here in a filter type star cell star. Okay, and you can see all the cell material cells. Copy the material to this selected zones, say okay to this. Okay, and then close it. Then select the next material, that is tab. Select any one tab over here. Okay, select any one tab, and for which again edit the properties and assign the aluminum, so which is default one, so no need to make anything. All these solid materials will have aluminum material, so no need to worry about it. I just need to go to next, that is the collectors connectors. So edit this, and for this we have to select the copper material. Okay, click on apply and close. Again copy this from this connectors, two remaining connectors. Okay, again types star con star, so that is CON star. So you can see all, and just copy it and close it. Similarly, we have to assign another material for the uh, end supports. Okay, so select the end support solid and just change the material to plastic. Okay, so edit, select the material to plastic, apply and close, and then again copy it from this particular cell support to other cell supports. Okay, so there is only one, so copy it to both and close it. Then next one is a fins. Okay, so select this cooling fin, and again change the material to aluminum. So aluminum is default, so no need to worry about it. Then last one is a foam. So select the foam material, select the foam material, foam parts, and apply the foam material to that. Okay. And similarly copy it from one foam to another foam parts. Now materials will be assigned with this. Okay, so as you can see, selecting to all, apply and close it. So materials are assigned to all the parts separately, and now we have to define the boundary conditions, like from the different locations. So we have to give the temperature conditions over there. I'm just moving it a little far forward. Okay, so for this, what you have to do is to apply the boundary conditions. What you have to do is select any two wall surfaces. Okay, and then just you will be option to go for multi-wall edit. Now these options are available only in the latest version of ANSYS, like from 2019. So if you are using old versions, you will not get this. Okay. Then go for convection, give the convection rate of 5. Okay, and select all the locations. So for all the location, convection heat transfer coefficient is 5. Okay, select all, click on apply. And close this. And now we have to select the specific locations where we wanted to apply the material properties. Okay, so here you can see we are applying the select all the wall function. First, we have to apply the adiabatic property to the fin surfaces, right? So here, select the fin, only display the fin part. Okay, so these all are the fins over here. And now select any two fins to go for multi-wall edit, and then give the adiabatic property to the fin surfaces over there. So there you can not adiabatic, I'm sorry, it's we have to give the heat transfer coefficient so that heat will transfer through this fin surface, right? So in the zones list, again select the wall fin, and then select all and give the heat transfer coefficient of 2000, and then it is done for from all the faces it is 5, and from the the fins it is 2000. Okay, so that is given. Now model is ready, so we have to solve only for energy equation and for the battery models. So just go to the solution, and in the solution you can go for the methods, and here in the options, the advanced options, so you have to in the equations part, you have to select only energy and scale 0, which is a battery model. So these two equations only you have to solve, otherwise it will take again more time unnecessarily. Then you can define the residuals over here. So go to the residuals, and here you can see residuals are 10 raised to minus 6 and 9. Change it to 10 raised to minus 10 and 10 raised to minus 12 over here. Okay, say okay to this, and then you can add the report definition. Okay, so volume maximum volume average, that we can track it. Maximum temperature in the complete model, and then maximum average of temperature on the cells, on the cell how much temperature is there, and again on the complete model. Okay, so these two things we are tracking over here. Then just simply start the problem solution. Okay, so average temperature on the cells, then most important thing over here is to save your file before starting the simulation. So in case any mistake you have done, software, there are chances of software that is going to get crashed. So better first, save the case file. That will be helpful for you. If anything happens, or if the system won't sustain this load, it will automatically restart or something will. So better you can keep a backup of case file every time whenever you are solving. Okay, so that can be helpful for you. And then start solving the model, and then you will be getting the results. Okay, now it has created the case file, and now we can give the number of iterations and solve. You have to initialize it before solving, and once the initialization will be done, then you can go for the number of iteration and start the calculation. Again, there are more different modules are available in the battery analysis, so you can learn them. So just give number of iteration 100 and start the calculation. Okay, so I have just stopped over here the calculation, and I have opened already existing problem. Okay, so the reason is like it was taking more time. Okay, so when it will start the iterations, so you'll start getting the parameters and everything. So you can say I have stopped this, and I am just opening the existing problem. Okay, it's like I have already kept this solved, that I am opening over. Yes, once the model is imported, so you can go to this graphics in the contour section, and you can create a contour where you can actually observe the temperature variation inside the complete battery pack. So static temperature, you can check it out on all the surfaces. Just click on save and display, so it will show you the temperature. Okay, so you can see this is how the temperature is varying inside this complete battery pack. You can see maximum temperature of 3.1 Kelvin, like 321 Kelvin that we are getting over. Okay, so you can say 321.2365, that is the maximum temperature, and 300 Kelvin, that is the minimum temperature that we are getting over here. Okay, so this is how we can do the thermal analysis of a battery, complete battery pack actually. Okay, so I hope it gave you a clear idea. If you have any questions or any doubts, you can ask. So that's all from my side for this session. If you have any queries, please.
Yes, participants, the platform is open to you. You can raise your query, your questions.
Again, in battery, lot of modules are there to learn. So many things are there to understand. So definitely, if you are interested, you can just go through that.
If you have any questions, your query, please ask.
So whatever we saw now, that was this CST analysis. Before that also cell CST is there, thermal abuse analysis, thermal abuse and CST combination, that is also there. Then PAC CST. CST is conjugate heat transfer analysis. Then again, if you're a electrical engineer, so these all part like ECM, module ECM, PAC ECM. So these different modules which are available for battery packs to learn. So you can definitely check it out.
Kailas, sir, there is one question.
Yeah.
Can SOC and SOH estimation can be done in ANSYS?
SOC. Yes, I think it is quite possible over here. This yes, both the things are possible in the ANSYS, and you can try it out. Both the modules are available. So state of charge and battery state of health. So mostly it can be done in the twin builder side. So which is a simulator where you can simulate all real-time condition and you can get a real-time data from that. So it is possible in the twin builder side.
Okay. Any other query? I guess many questions were asked during the session itself.
Yes.
And you had answered them at the same time. One question, sir, I would like to ask. Some in news I had read about this battery management system software. This electrical vehicles, especially I read news about this Tata Nexon EV, that sometimes that battery was showing some 2% charged, and sometimes it was showing 53% all of a sudden. And sometimes they were, when they started their vehicle, they kept the vehicle at some 53% off, and when they switched on again, it suddenly shows the drop of the battery. But it was not an actual case. The battery was still there, 53%. So their technical person said it was something related to battery management system software bug.
Yes. So that could be like maybe some malfunctioning of some sensors over there, we can say, or that could be the some programming that is I can say I'm not that much into the BMS, but if Vivek is there, I think he can answer it. But yeah, it mostly because of the sensor malfunctioning or whatever, there should be some bug in the program itself. So that could be the reasons behind that.
Right. Okay. So since no questions as of now, thank you, sir. Thank you, Vivek, sir. Thank you, Kailas, sir, for such a.
Sir,
yes, sir. Please. Yeah.
One feedback we need from for us as well. So I am just sharing the.
Yeah, sure. So participants, there are two types of feedbacks here now. There are two different links for the feedback. Right. One, Kailas sir will be posting one link, and one will be from the AppSheet. All participants are requested to please make sure that you give feedback in both the links.
Sir, I just request you to post both the links in WhatsApp group. Is it possible?
Admin.
I'm very now.
Oh, sir, do one thing, Kailas sir.
Yeah.
Yes.
You please send your link personally to Amol sir.
Okay.
And we'll post that link in that other group.
WhatsApp.
Yeah, because here there are chances someone may only put up only one feedback, and they may leave the meeting.
Okay. No issue.
Yeah. So still, if someone are interested to give the feedback here itself, there is one link given here. Please make sure you are submitting both the feedback Both feedback are very important. Okay, thank you, sir, for such an informative session. You explored and thoroughly gave insight of the battery management along with simulation software approach. Kailas sir very smoothly blended the information and gave knowledge of battery thermal management with ANSYS. The way you both explored and refined the in and out technical know-how of the battery was something which each participant will find helpful in long run and may find it beneficial in a coming future of electrical vehicle area. Also, the presentation slides were very informative and self-explanatory. Once again, thank you so much, sir. We expect your presence with us in future too.
Sir, we'll take photo.
Yeah. Participants, please switch on your camera.
Hello, sir, can you just stop the presentation?
Yeah, yes.
Thank you.
Sir, once it's done, please let me know.
Done, sir.
Okay. So participants, we conclude our second session of day 2. We'll meet at 2:30. Right? Please make sure that you people are all there before the time. Thank you so much for joining this session and being an active participants. Thank you so much.
Thank you so much, everyone.